Oh, there we go. Sorry about that. Oh, and I didn't. Let's see. All right. So for the data link, I'm going to upload it to Google Drive because I didn't realize you have to actually make an account to get this Penguin data. Um, and you should actually already have it in your data folder. But let me just upload it for you guys, just because that will be a little easier. So 1 second here. We're going to be covering decision trees today. Sorry that you're kind of just watching me do this. 1 second, 1 second. Data courses, another master class. Um, Data, and then penguins enter, penguin size, and this guy will be. Whoops. Trees. All right. All right. I'm just gonna upload it. 1 sec. Sorry. I was trying to figure out the Steam key or stream key, and then it wasn't connecting for a while. You're watching me do a bunch of stuff. I bring out live streaming. Alrighty. And as I mentioned before, usually the stream takes a while to catch up, so you may want to like rewind a little bit. Um, okay, and then 1 second, we're going to upload this data set to Google Drive for you. If you have the notes, you should actually already have this CSV file. Show file location. What we're going to do is get link. There we go. And let's go back to YouTube to paste it. All right. So that's the data we're going to be working with. You can download it right now or download it later. You also already have this CSV file in your data folder if you've downloaded the zip that goes along with the course. But just in case you don't want to open all that up, you can just hit this link. I'll talk about this data set later on. But what we're going to cover today are decision trees. So I kind of say tree-based methods here. I'm going to briefly cover a little bit of the history, just because in some of the history slides we discuss how the first decision tree was actually constructed back in the 60s, and it's kind of useful to know that. And then we'll talk a little bit about kind of the key important idea behind decision trees, which is how we actually decide on splits, how we decide on the ordering of nodes. It all has to do with information theory, and we'll specifically cover the version called Genie Impurity. And just to check right now, it looks like you're about maybe 30 to 60 seconds delayed in the stream. As I mentioned last week, that will usually go longer and longer as time goes on. And just in case this is anyone's first time on the streams, you can always chat with me, and the chat is instant, and I can respond through chat if I need to get you some information. Are you sure there's no link? It should be this. You mean the Google Drive link doesn't work? That's weird. No, the link is there. I just pasted it. The Google Drive link? Maybe someone can tell me if they've seen that drive link. Um, it's not showing up. What the heck? Maybe it's being blocked? That's weird. What the heck? I just... So you guys can't see that I'm pasting this Google Drive link right here? That's so weird. Um, maybe it blocks Google Drive because it thinks it's like some sort of virus or something. I'm not sure. Um, this is crazy. I guess go. Well, we'll cross this bridge when we get there. But I don't know. I'm literally just copying and pasting it. I don't know if you guys can see it, but I'm. What the heck? Copy link. I'm pretty sure we've done this before. Okay, so I'm guessing YouTube chat is blocking the Google Drive link. Let me try a URL shortener to get you to the same link. Maybe that will work. Yeah. I'm gonna try a URL shortener right now. Do you guys see that link? And Kingbuck, I think he wrote yep. Maybe too early. Does this link? Whoa. Okay, I guess I'm being blocked from all links. What the heck? Alright, I'm gonna paste it in the slides. It's crazy. I'll have to see if that happened. Yeah, it's the Palmer Penguin. Penguin. Okay. Sorry about that. That's so weird. I'm not sure what's going on with those links. I haven't encountered this. It was working fine last week. Maybe it's something on my settings, but I feel like on my own channel I should be able to chat the thing. But anyways, it's this. And just keep in mind, you'll probably have to pause it here. From my experience, Bitly is case sensitive, even though like that kind of in theory doesn't make sense. I believe Bitly itself is case sensitive. So it's bit.ly/2 capital K capital F V W UA there. So you can get this data. You may want to just pause it, get it. It's also called the Palmer Penguin dataset. You should be able to Google search it and find the CSV file of it. But apparently any link I post is being blocked. It's like ghosted. I don't know. That's so weird. I'll have to figure that. I don't know. It's kind of interesting that they're doing that. I wonder if any of you can post a link, or if it's. Anyways, that's so interesting. Okay. So I'm going to move on. If someone needs to see this link, they can just pause it here. Let's go through a little bit of the history of decision trees, kind of how it came about. We'll also talk a little bit of information theory, not a whole lot because this is not some science class from the 1960s. And then we'll talk mainly about genie impurity. That's really the main thing you have to understand for decision trees. And then later on you can revisit in this course. We'll start uploading a bunch of tree-based methods this week. So this week, as far as the uploads to the course, we're going to be uploading decision trees, random forests, and then gradient boosted trees, sometimes known as just like XGBoost or whatever. Okay, so let's talk very briefly about the history of decision trees. I'm going to go a little faster through some of these slides than I will in the course. So just keep that in mind. But basically, there's a couple things I want to point out when we're talking about decision trees. When we're talking about decision trees for machine learning, we're actually talking about kind of a very specific term called statistical decision trees. Nope. Okay. So just be careful to note that, because if you do a Google search for decision trees, it will take you to the wrong page. I just kind of want to show you that right now. So if I do decision tree, if you say, oh, let me Google search decision tree, and you check out the Wikipedia page for decision tree, it's going to take you to the wrong type of decision tree. So just pay attention here. It says like, oh, this is a support method, and this sort of method has been around a lot, especially for probability. If you want the Wikipedia article, it's going to be decision tree learning, and this is the actual machine learning decision tree. So keep that in mind. If you're doing a Wikipedia article and you're looking for a lot of these ideas, it's decision tree learning, not just decision tree. That's what we're talking about here. So the term decision tree has been around for a long time, but when I'm talking about decision trees here, I'm talking about this kind of very specific statistical learning model that was developed in the 1960s. So let's talk a little bit about that, because clearly anyone can just kind of draw a mapping of a decision tree on a piece of paper and say like, oh, I have a pretty good idea. So in general, the term decision tree can refer to a flowchart mapping out outcomes. So this is, again, not what we're talking about. I'm not talking about, oh, what's the probability that this happens? I make it a heads. Probability that that happens, I make it a tails. What we're talking about is an actual decision tree, which is a statistical model, where the node splits are based on, and this is the key term if you get anything from today's stream, is that it's based off the information metric. So I really want to dive deeper into this idea of this development of the information metric and how it leads to the ability to create decisions based off predictions. Okay, so fundamentally, pretty much all we really want to know about decision trees are how do we decide on the ability to split features as we continue down a tree, and how do we actually construct this tree? What does it look like? And the main idea here is the idea that I can actually mathematically measure information. Okay. So, how do we actually measure information mathematically? If you've never heard of Claude Shannon, he's known as the father of information theory. And this guy invented and developed a lot. He's kind of at like an Einstein or Newton level, but for some reason he's just like not as famous, at least outside of computer science. And so he publishes the journal article, A Mathematical Theory of Communication in 1948 in the Bell System Technical Journal. And it's actually so fundamental, and I think this kind of is telling of how important this is. It's later republished as a book, and they changed the title to The Mathematical Theory of Communication, which is kind of funny. And so he actually worked in many fields. So he developed basic circuit design, essentially starting to develop how do you convert something like Boolean logic to be computed by an electrical circuit? How can you use resistors and capacitors to actually map that out? It's essentially kind of the first computers. He also worked in cryptography. He actually met Alan Turing, so his work was with the US Navy, helping to kind of decrypt Nazi codes and Enigma, so he actually worked on that, met Alan Turing. He also met Einstein at a certain point. Wearable computers, he worked with Ed Thorpe, who is kind of the father of quantitative finance. And with wearable computers, he actually invented the first one, and it was to try to predict where a roulette wheel would spin. And so now if you go to a casino, there's rules against wearing computers to aid you in playing the games. So he kind of stemmed that. And then he also helped develop kind of the very first artificial intelligence systems. He's kind of famous for building out this little mouse that could solve a maze, this little robot mouse. So yeah, he's kind of like the Forrest Gump of computer science if Forrest Gump was incredibly smart and was essentially a genius because he runs into all these famous people throughout his life, and he's also a goofy guy, like was on a unicycle, would juggle. Really interesting person. Okay, so anyways, we have the ability to measure and define information. That's going to become more important as we learn the mathematics of how this is actually constructed when we talk about genie impurity. So I'm just going to quickly go through the decision trees and how they're developed and constructed. We'll go through some of these slides, but the one that we really want to go through is essentially the statistical decision tree process is first published in 1963, and it's a form of regression. So what's kind of interesting here is when a lot of people think of a decision tree when they're first learning about it, they learn about it for classification, but in its development, a regression tree was first created. So that means they built a tree to predict a continuous label instead of a categorical one. And it's actually a lot easier to do that, which is why it was developed first. So this guy, Morgan and Sonnquist, they created what's known as the piecewise constant model with splits for the decision tree. And so this is essentially what I want to show you on how this actually works for the tree they created. And then we'll talk about that genie impurity, as well as of a couple ideas and vocabulary terms we want to discuss. Okay, so let's imagine that we have a single X feature and we want to be able to predict a Y outcome. And we have these set of training points. So I have some X feature, it goes from 0 to 3 in this particular data sampling, and it goes from 0 to 3 in the Y direction. And we can kind of see it's following this curve, and maybe this is really difficult to model with a polynomial regression because maybe I'm starting to overfit or something. So I can see it kind of fits that curve, but in reality, I don't actually have that curve. I have these points, right? So how could I build a regression tree to try to actually model this out to form predictions? That way, in the future, when I get an X value, like let's say I get an X value of 1.5, I'd be able to predict what the appropriate Y value output should be. So the way this works is the decision tree is going to get your features and it's going to start doing splits on them. And so in 1963, what they started to develop was just a very simple model that would split up the X features, and we'll talk about how they actually decide these splits later on in just a second. But they would do something like, okay, let's take a look at the features of X less than 1. And then what we're going to do is we're going to say, what's the average values of those training points that we already have? So we're going to say, is X less than or equal to 1? If that's true, I'm going to predict my output of Y is equal to 1.5. However, if it's false, then essentially I'm going to now have another decision section. And now this decision section is X less than or equal to 2? In reality, this is actually now kind of a range, right? It's X between 1 and 2 because I already have, let me get my pointer here, I've already done this decision that's going to have this output. So that's what this line is. So if X is less than or equal to 1, I'm just going to output the prediction of 1.5. However, now I'm discussing this range. What about X less than 2, but not less than or equal to 1, so essentially between 1 and 2. Well, I'll take a look at my training points, and I'm going to average out those values. And I'll do the same thing for anything greater than 2, right? So if X is less than or equal to 2, I'll predict that the value is maybe around 2.2. If it's false, essentially X is greater than 2, I'll predict that it's 1.5. And now you can see I'm starting to develop these average outputs for my model. And then I can just kind of make connecting lines. And this is why whenever you see something like random forest regression or decision tree regression, if you just look up those images, they're always like kind of these squarey step function looking things. And that's why, because we're essentially limited by how we can split the feature data. So if you see something like, let's see, decision tree regression, 1 second here. So if you ever do a Google image search for decision tree regression or random forest regression, if you actually see the regressions themselves, you'll notice they're always kind of these blocky, squarey looking things. And that's just the nature of the algorithm because it's based on how finely it's splitting up those features. So keep that in mind. You'll always get this sort of behavior. Granted, if we were to make x super tiny, like x between 0 and 0.1, you could start to really smooth this out by getting these tiny little steps. So that's not to say it's going to be hugely blocky, but it will, fundamentally at some level, also in multiple dimensions, be this kind of like weird step-looking function thing. So I just showed it to you with one x feature. This is what it would look like with two x features, right? You can see here we're starting to block it out. So that's why you get that behavior of what I'll call blockiness, in case you were always wondering why that was whenever you saw these. Okay. So in that 1963 paper, they say, I'm going to decide the splits at each node based on what they called node impurity. And it was actually just defined as an error metric. It was essentially, what's the difference between my output versus my predicted output squared. And this is very similar to like root mean squared error or mean squared error, etc. All right, and now I'm going to kind of go a little faster through the history here. But essentially, in 1972, these two guys, Messenger and Mendel, they published the first classification tree algorithm. Notice that it's almost 10 years later that they figure out classification. That's kind of telling how much harder that problem is, because it's really easy to measure your error and your splitting for continuous variables. You just say, okay, less than or equal to. But it's a lot harder when you have something like green, blue, and red that you have to split. That's really hard. Like, how would you actually measure that? And we'll talk about that with genie impurity. But what they called their condition was theta automatic interaction detection. In 1974, they published a general algorithm. I should probably fix that. Then in 1980, Gordon Cass publishes a technique on top of this. He's basically further building on top of that work. He calls it the chi-square automatic interaction decision. So we can see we're just building off on top of this. And really, the big leap is while these publications are going on, there's two professors at Stanford and two professors at UC Berkeley, and they're actually writing a book that they call CART, which stands for Classification and Regression Tree Based Algorithms. And then they publish in 1984 the book. And I think I see a lot of confusion here by beginners. They think of CART as just like a general methodology, which it kind of is. But in reality, it's actually this book and this set of software that's published in 1984. And CART is just a huge leap forward from all the publications in the past. The publications in the past, a lot of it was just for kind of like small sociological data sets. And now, with the publication of the CART book, they have a lot of improvements on practical usage of the decision tree algorithm. And in fact, pretty much these methods are what scikit-learn uses, these CART-based methods. And so here's the actual book, published in 1984, Classification and Regression Trees. You can see their four names there. Excuse me. And it introduces a lot of concepts. It talks about cross-validation for trees, pruning trees. If they get too many leaves, we'll prune them down, and I'll talk about what that means. Also talking about things like search for linear splits, variable importance scores. So it's kind of it's a set of software rules as well as a set of the concepts and math behind them. So a lot of work is done with this book, and suddenly classification regression trees are practical because they released the software. Granted, it's the 1980s, so it's not like scikit-learn yet. But they also, more importantly, released the book, and this kind of blows the door wide open on, oh, we can actually use this stuff for any data set, not just these kind of sociological journal studies. And then, just to kind of finish this off, there's this guy called John Quinlan. He developed something called the ID3 decision tree algorithm, and essentially what he did here is he's switching out what he's using as information criteria. Instead of genie impurity, he's using something called the gain ratio. He improves on it again with C 4.5, which is actually still very popular. That's in the 1990s. And then sometime in the 2000s, he releases a really highly optimized commercial version called C 5.0 with various improvements. So what John Quinlan is doing, or he's also known as like J. Ross Quinlan, he's just figuring out what's the best idea for splitting. How can I measure that information? And then if you take a look at the Wikipedia page, it'll actually show you beyond this. It talks about the different methods here, but it also talks about the metrics. Because really, at the end of the day, the algorithm is just how do I decide on what to split? So it talks about genie impurity, which is what we're going to talk about today. It's probably the most common one. But it also talks about information gain, which is what John Quinlan essentially figured out. He kind of took this concept of entropy from information theory, which is what Claude Shannon was working on. So if you take a look at information entropy, eventually it should link you back to discussions of Claude Shannon here. So he introduced it in 1948. So it kind of all circles back to Claude Shannon, which you can keep circling back to someone else, which has to do with like the term bits of information. I think Claude Shannon was the first person to officially publish a bit as an idea, like a bit of information. And I think he later actually credited that idea to the guy who invented fast Fourier transforms. I think his name is Tukey or Tukey. Anyways, okay. So let's actually move on to the fundamentals of a decision tree now that we understand just a little bit of the history. I think it was important to understand that the regression tree came first versus the classification tree. And that it was invented not too long ago, right? Like 1984 is not that long ago. And if you have any questions at this point, you can type them in the chat, although I'm not a history expert in this, but maybe I'll know something. All right. So last two things I want to talk about is the basics of the terminology I'm going to be using. That way I don't have to keep pointing at stuff. And then the genie impurity, how it actually works. So to begin understanding a decision tree, I want to first review just some quick terminology components. So recall this very simple regression tree that we constructed, right? I want to talk about what I actually call each of these things that's happening here. And you're probably already familiar with a lot of these. So what is splitting? It's pretty straightforward. It's when you're actually splitting the data. So you're taking the entire data set and splitting it based off a feature condition. So here I'm taking all my data. In this particular example, all my data was just two columns, right? My X and Y. But I was splitting it based off X less than or equal to 1 versus greater than 1. So we're taking the entire data set, which is often called Q, and we're just keep splitting it. Genie impurity, so there was a quick question in chat, is which one's the easiest? I would say genie impurity, and we're actually going to solve genie impurity in an example in just a second. Okay, nodes. I think it's kind of obvious what the nodes are, but these are all nodes, right? It's either what feature is being split or the result. So let's talk about the different types of nodes. There is the root node. Root node can be thought of as the most important node because it's the very first node that you split on. In this case, I decided to split on X less than or equal to 1. And we'll talk about later on how we actually decide, how do we decide which feature should be the root node. Clearly the root node has a lot of power because that's the very first thing you split on. So in a sense, that's the feature that's going to have the most signal or decision-making power. So that's the root node. There are the leaf or terminal nodes. These leaf nodes or terminal nodes, that's the end of the line. That's why it's called terminal. It also looks like a leaf from a tree. And essentially, that's going to be your output prediction. That's going to either say, I think the Y value should be this for a continuous label, or it's going to say, I think the output should be this class if it's categorical. So say, oh, I think everything that ends up at this leaf node should be the color blue as my prediction, or something like that. So obviously I can then, what's really nice about decision trees is they're extremely interpretable by a human, right? You yourself could just come with a data set and go, okay, come here to this, answer this question. If it's false, answer this question. And then suddenly you'll end up at your decided prediction. So if you had a new data set with one X value, hey, I have an X value of 3. What should it be? You would just say, okay, is 3 less than or equal to 1? No, it's false. Is 3 less than or equal to 2? No, it's false. Okay, my predicted output is 1.5. Parent and children nodes. We're not going to use this terminology too often, but it's just the idea that you have a parent node, and the children are the nodes that stem off of it from a split. So we actually have two sets. We have this parent, these two children, and then you could say you have a parent here and these two children. Tree branches is essentially a subtree, right? So you could think of this entire set as a branch off a tree. And hopefully you can now begin to see the analogy of a real tree and leaf. It's quite fitting for what we have here. Pruning is a concept of cutting off here. So pruning is essentially shortening the tree to try to avoid overfitting. You can imagine that as your x's, in this particular case, as the ranges get really small, so like we could have a really complex tree that said x in the range of 0.0 to 0.1, x in the range of 0.1 to 0.2, etc. So you could have like hundreds and hundreds of nodes to get this really choppy regression line. Now, is that necessary? No, because that could lead to overfitting to the training data, right? So maybe you want something a little smoother with not so many steps. So what you could do is do pruning, which essentially says, you know what, I think these two are overfitting too much. Let's have this be a terminal node instead. So we prune off these terminal nodes and say, kind of take the average of these guys and just leave it here. So this is known as pruning. This is kind of an extreme case of pruning because the tree was not that huge to begin with, right? But it's just the concept of taking leaf nodes and deciding this is probably overfitting. I'm going to cut these off and send it back up to their parent node and have that be the final leaf node. It essentially makes your tree shorter. And obviously, again, pruning, terminology that's stemming from trees, like real life trees. Okay, now I'm going to move on to constructing a tree. And when I say talking about constructing a tree, I'm really just talking about genie impurity. That's really what I just want to get across here. And then we can play around with the different factors that are available to us within scikit-learn. All right, so what I really want to talk about is just exploring how a decision tree is constructed using genie impurity. So when we're first constructing a tree, the very first thing I have to decide is what feature is going to be used as a root node. And what we can actually do is use genie impurity to compare the information contained within features for the training data. Basically, how useful is it to split on this feature first versus that feature first, etc. So this is where we start to get into the math. But luckily, the math is actually pretty straightforward. I think coming up with the math was really hard for some of these people. It took basically a bunch of like math geniuses to figure this out. But when you actually see the math, any bozo like me can actually do it. So this is genie impurity for classification. And the way it works is it says for a set of classes C for a given data set Q, where P of C is the probability of class C. Now, this looks kind of hard to read, but it's not so bad. What we're going to be doing, and we're going to work through an example of this, so don't worry if you don't understand it quite yet. Essentially, all we're going to say is genie impurity is what's the probability you belong to the class times the probability that you don't belong to the class, 1 minus P. And you do that for all the classes in your data set. And you can just plug in this in order to figure that out. So it becomes essentially like a weighted average. Now, we'll actually show this because I think it's just easier to understand if you go through the math. So take a look at this data set. Very simple. Again, I'm just dealing with one feature for simplicity here. Otherwise, it would take me forever to plug in these numbers. And then I have a Y spam. So essentially, what I'm trying to figure out here is I want to create a decision tree for detecting spam in an email. And it's actually kind of goes in line with the issue I was dealing with Google Chat today. And we can think of the Google Chat instead of email. But essentially, I'm going to say, my feature is, does this email contain a URL link? Yes or no? And then, was this training data labeled as spam? So I had a human read a bunch of emails. In this case, they read 7 emails, right? And they checked, did this email contain a URL link? Yes or no? And was this a spam email according to this person? And I only have one X feature to use for a node. So right now, we're just going to go through genie impurity as far as how to decide the split itself, and then we'll talk about if I had more features, how would I actually rank these root nodes. So how do we actually do this? I need to first do a split in order to predict if an email is spam if it contains a URL. So how would this work for kind of the simplest case where I have just one feature and one label to predict, and they're both actually yes or no. Quite convenient here, but this is for the math as well. So what I'm first going to do is answer the question, does this contain a URL? Yes or no? So if it does contain an email, or excuse me, a URL link, true. That's what I have here. Notice, predict if an email spam contains URL. I asked the question, did this email contain a URL? In this case, 3 of the emails in my training set contained URL. However, let's see, so that's the true there. Let's see how many of them were actually spam. 2 of those were spam emails, but essentially I have what's known as a misclassification occurring here, right? One of the emails I had that contained a URL link was actually not spam. Maybe it was a coworker sending a useful Google Drive link and they couldn't send it. So right now, I see that my URL feature, if I split on it, I can only split yes or no, but on that splitting, I will have some misclassifications. What about the other way? What if it did not contain a URL? So here are the cases where it did not contain a URL. There's 4 cases that are no, that it did not. So over here, the total 1 plus 3 is 4. And then in this particular case, if it did not contain a URL, how many of these were spam? I did have 1 spam email that didn't have a URL, but was still spam. It was trying to sell me something. But for the most part, if it didn't contain a URL link, for 3 of these, it was not a spam email. So hopefully you can see how those kind of ratios make sense, right? Kind of the odds are 2 to 1 if it did contain a URL that is going to be spam, versus 1 to 3 if it did not contain a URL. All right. So what do I do with this information if I actually want to calculate genie impurity? So recall the genie impurity formula. Essentially, what I'm going to do is I'm going to try to answer the question, what is the genie impurity of the URL feature? Basically, trying to answer the question mathematically, how useful is this feature for splitting on? How much information is contained in this feature? So what we do is recall, I'm doing it for a set of classes. So I'm summing this up over the set of classes C. And how many classes do I have here? I have 2 classes. Either it's spam or it's not spam. So that's 2 classes. So let's start by calculating the left leaf node here. So I'm just doing the math for this left leaf node. And what we start off with is saying, what's the probability that it is spam? So we'll say class 1 is that it is spam. So probability that it is spam, if it does have the URL as true, this is the left leaf node's genie impurity right now, and then we'll take the weighted average to get the URL genie impurity, is going to be 2 out of 3. So that's where this 2 out of 3, because that's the probability that your spam if the URL is true. So then that's 1 minus the probability of being spam. But recall, I have to do this for the sum of all the classes. So what's the other class? It's not spam. So I'm going to add it in for not spam. What's the probability of being not spam if it's true on URL? Well, it's essentially the reverse, right? It's 1 over 3. And then here we're going to say 1 minus 1 over 3. So take a little bit of time. Oh, my face is covering this formula. Sorry, in the stream. Maybe I moved my face. 1 second. Whoop. There we go. All right, sorry about that. I kept pointing at this screen. I think that will update in just a second. All right, so just going to go over that because I didn't realize my face was covering this. Again, what we're doing here is we're simply following this equation for each of the classes. Where each class, there's only 2 classes in this case. It's what's the probability of being spam, what's the probability of being not spam. So if URL is true, the probability of being in spam, if URL is true, is 2 out of 3 times 1 minus 2 out of 3, just to follow the formula. Next class, what's the probability of being not spam? That's 1 out of 3. So essentially, you just have to figure out PC for each class, and then plug it into this formula, and then add them all together. That's what genie impurity is. It's simple as that. So if you were to actually calculate all this, you get around 0.44 for the genie impurity of the left leaf. And let me know if you have any questions in the chat, because this can be a little confusing the first time you see it, but I think if you just kind of follow the logic of figuring out probability of belonging to each class, it's pretty straightforward to go through the math. So if we were to do the same thing for the right, this should be leaf node, not lead node, sorry for the typo. So if we do the same thing for the right leaf node, we'll say, okay, what's the probability of being spam if you're in the right leaf node here? Well, that's going to be 1 over 4. So that's PC, 1 over 4, of belonging to spam. What's the probability of not belonging to spam? Well, that's 3 over 4. And so that's where we're getting these numbers from. All you have to do is calculate the probability for each leaf. Okay, hopefully that's not too complicated. You can see here that it's just a measure of the probabilities of belonging to each class, and then you're summing them up based off this formula of probability of belonging to class times probability of not belonging to the class. And you do that for each class, and that's the impurity. And hopefully you can begin to see kind of just intuitively how this could be a information metric of how useful is this information of actually reporting back what class could be correct. And I think something that's usually helpful is if in your mind you take this to an extreme level where probability of C is 0, probability of C is 1, you can see that if probability of belonging to a class is 0, one of these will immediately become 0. If probability of one of these is 1, this will become 0, so you'll end up getting 0. Okay, so that was the probability of the leaf nodes. I still need to answer the question, what's the probability of the what's the genie impurity of the URL feature? So I have the left leaf genie and I have the right leaf genie impurity. So now that I have these two genie impurities, I can use the weighted average of them to get the genie impurity of the URL feature. So I have my left leaf genie impurity and my right leaf genie impurity. I also know that there's 3 emails on the left leaf and 4 total emails on the right leaf. So for the weighted average, I'm just going to take the genie impurities and multiply them by the ratio of the emails versus total emails. So recall the total emails I have is going to be 2 plus 1 in the left node, and then 1 plus 3 in the right node for a total of 7 emails, right? So 3 plus 4 is 7. So I have 7 total emails. I also know my left leaf genie and my right leaf genie. So I have these numbers here. I also know how many emails total I have in the left. So left emails are a total of 3. Right emails are a total of 4. Now all I need to do is take their weighted average. So what I'm doing is I'm saying in the left node, I have 3 out of the 7 emails. I'll multiply that by the left leaf genie impurity. And then in the right node, I have 4 out of 7 emails. So I'll multiply that by the right leaf genie. And then I have the genie impurity for the entire URL feature, which is 0.403, roughly about that number. And now that's how you calculate the genie impurity for just a feature. You would kind of treat that feature as if it was the root node. So now I have a genie impurity for the URL feature. But what if we actually had multiple features? Essentially, the question then arises, how would you decide on what the root node is? And it's actually really simple. You would just repeat this process for all the other features that you could potentially have. So let's say you have another feature that maybe doesn't say URL, but it says, was this sent from an email within the corporation? Like, was it sent from at mycompany.com or something like that? You would repeat the entire process for that particular feature. And then you would do that for all the features. The one that had the highest genie impurity would then be your root node, because that's essentially telling you this has the most information. Okay, so there's still a lot more stuff to consider, and we won't go through the slides here. I think, did I say highest? It should be lowest. Okay. So we still have more features to consider, multiple features, continuous features, multi-categorical features, lots of stuff to consider. And so what we're going to do now is switch gears. You'll have these discussions in the course itself. We'll go much deeper into all of these. But I kind of want to switch gears, make it a little fun. And so we're going to deal with that Penguin data set. And then we're going to actually show you how scikit-learn does this. So let's do that. And so now what we're going to do is I'm going to work through this notebook here. But I'm actually going to start a new one. I have a new notebook, untitled. Oh, and you can see here, this was my work, trying to calculate the impurity for the slides. Okay, I'm going to delete these, And let me open up a new notebook real quick in my incognito window. I think I had one here. There it is. All right, so what I'm going to do is kind of work through this example. Sorry, I'm going to move these a little bit around so I can see everybody. As far as these lectures, we'll probably I was trying to plan them to release all the tree-based methods at once, but we'll be doing it throughout the week. So you'll see decision trees probably Monday and Tuesday start coming out. Then you'll see random forest coming out, and then you'll see boosted trees coming out. But really, once you understand decision trees, you kind of understand all of them. It's more like a set of rules on top of decision trees. It's implemental improvements. Okay. So in the chat, what I want to ask here before we continue, was everyone able to get that penguin data set? What's crazy is I can't link anything, which makes this really hard. But you did see, hopefully, that bit.ly link. I'm going to copy and paste it one more time, just so you can see it here, just so I can confirm that it's working. So the bit.ly link should be this one. So that is the link of the penguin data set that we're working with. You should also be able to look up the Palmer penguin data set. So if for some reason you're not having success with this, just Google search Palmer penguin data set, maybe CSV file, and I'm sure you can find it somewhere on the internet. Okay, cool. Thank you. Hopefully this is, what was I going to say? Oh, I'm sure you're all familiar with the iris data set. What people kind of want to do in the machine learning space is move away from the iris data set into the Palmer penguin data set, just because I think his name is Fisher. The guy who created the iris data set is actually like not a great person. He's like kind of super racist. So they kind of want to move away to a gentler data set. So that's why we're using the Palmer penguin one. And hopefully in the future, that kind of gets... it also has like just better features to play around with. Okay, so what do we have here? Just to kind of show you, we have these cute little penguins, right? And essentially what we're going to be doing is we're going to be saying, can I predict what kind of penguin I'm looking at based off measurements, right? So I have a team of researchers. They go to Antarctica or wherever the heck these penguins live. They measure their flippers. I think they also measure their beaks. I'll see that in a second. They collect a bunch of data. And so now me as a tour group, I can now take measurements, and then hopefully my decision tree algorithm can tell me, oh, you're looking at this species of penguin. So we have this Palmer penguin data set. And so let's play around with it a little bit. This should also be in your data folder already, I believe. I think I already uploaded it in the latest upload. So what we're going to do is open this up and let me do some imports here real quick. I'm going to import numpy as np. Let me zoom in one level more. Zoom this guy out. All right, and then pandas pd matplotlib, matplotlib dot pyplot as plt, import seaborn as SNS. I think I saw somewhere in the chat that somebody was having issues importing stuff. In general, you should be able to use the base environment for Anaconda in order to import these libraries. Like, to be honest, we only really use 5 libraries, right? NumPy, Pandas, Matplotlib, Seaborn, and scikit-learn. And I'm almost positive those all already come with the base environment. So they should just work. So check that out. Okay, let me read in that data set. I have it stored underneath my data folder. So say pd read CSV. It's underneath my data folder. You may have to put in the full file path or wherever you saved it. So obviously your string here may be different than mine, right? Then I check out the head of this. Okay, so what do I have here? I have the species of that penguin, the island that penguin was found on, and then I have the body mass, the sex of the penguin. Notice I have some missing values here. I have flipper length, and then Coleman length, which I can't remember if I wrote down what that actually was. I don't know about birds. Let's see. It's the upper ridge of a bird's bill. Okay, whatever the heck that means. Oh, here we go. So it is this part of a bird's. And this person is tweeting. I think this is the woman who is really pushing for this as the next data set. So there's kind of a lot of cute pictures of these penguins. But this is the Coleman depth, and this is the Coleman length. All right, so we have a bunch of information about these penguins. And so what we're going to do is see if we can begin to create a decision tree algorithm for this. However, I'm going to do a little bit of data cleaning here. Obviously, there's some issues if I'm missing stuff. So I'm going to kind of rewind. That's what is also nice about this data set. It's kind of realistic as far as issues you may have to deal with. So it's not a perfect toy data set. So let's actually kind of go through fixing some of these issues here. So what we have to check is, am I missing any data? And so what I'm going to do is say df, excuse me, df is null or is NA, either is fine. And let's take the sum of this. So what this is going to do is, if you take a look at df is null, it presents a bunch of booleans. It's true if it's null. So if I could sum up these columns, it's going to treat each true as a 1 and each false as a 0, which in turn just reports back how many you're missing. So I am missing 2 rows of Coleman length, 2 rows of Coleman depth, etc. Flipper length, body mass, I'm missing 2 rows. And then sex, looks like I'm missing 10 rows of that. So while I ran this, it showed df head is not defined. Check your code. You need to read in the CSV. How many rows are in the dataset? Let's check. It is, without dropping anything, there should be 344 rows. And then columns, 7 columns if you include the label column. Okay, so how do I deal with this? Well, what I could do is just drop them. There's nothing too crazy here. You'll notice that for some of these, they're missing all the values, right? So what I'm going to go ahead and do is check out what percentage would be dropped if I just said df drop NA. So if I have 10 rows out of 344, is it a big deal to actually drop all these? Let's find out. I'm going to say 100 times 10 divided by 344, run that, and in this case, it's about 3% of my data that I'm missing here. And for, I think, 2 of these rows, you're essentially missing all the information. So there's no reasonable assumption you can make for how to fill in this particular value, because you're missing everything minus the island you found this person on. It doesn't really make sense to try to fill in this particular penguin's Coleman length and flipper length, because you don't know anything about this penguin, right? So what I'm going to do here is I'm just going to drop these rows. It's only 3% of my data, not a big deal. I don't need to be too clever about this. I'm going to say df drop NA. And now if I take a look at df info, actually let's say df is null dot sum. Okay, so kind of did a quick little dirty fix, but it wasn't too bad, right? Dropping 3% on my data is not so bad for what we're trying to do here. And I don't want to be like super clever in trying to figure out the sex of these penguins that are missing. Maybe if I had someone here that was a penguin expert, I'd try to figure out some formula for it. The last thing we have to check out is the unique factors for the categorical columns. So if I say df head, notice here I have, where is it? I have island as a categorical feature, and then I have sex as a categorical feature. You could, as far as the question of King Bach has, how would you check if some nulls appear in the same rows? Recall that you can always do this df transpose, and it would set these guys. So then you could say, start counting based off the transposition. So is null, sum, and you can start getting clever of like where it's greater than 0, etc. Notice this is all false, so you would just transpose it and start exploring it that way. Okay, what was it saying again? Oh yeah, we want to figure out the unique islands. So how many islands I'm actually working with here? Let's check it out. VF island. Unique. Unique. Ah. All right, there's 3 unique islands. And then let's check out the other categorical column. Recall the other categorical column I was dealing with was the sex column. So we'll say df sex dot unique. And you'll notice an issue here is there's male, female, and it looks like instead of a null value, there was actually some weird placeholder for a dot. So I have to figure out how many of these rows are actually affected by this. So let's see here. I'm going to say where are the rows where sex is equal to this dot column. And it looks like it was just one penguin. So for whatever reason, this one penguin, they accidentally put a dot in instead of its sex. So I have 2 options here. One, I could decide this is just one row, one freaking penguin. I'm just going to drop them from the data set. Or I could try to be super clever and figure out based off this body mass index, this is like a heavier penguin. It's more likely to be male based off its flipper length, etc. That is also a pretty reasonable approach here. Since this is a live stream and I don't want to figure all that out, I'm just going to drop it. So we'll say this. My data frame is equal to data frame where I actually know the sex. So we'll say where sex is not equal to this dot. I could have also said df drop this particular index location at 336. This is one way to do it in case there was more than one. So now if I run the exact same command, where sex equal to this period, it doesn't show up. There's no more. So that's kind of a way to filter that out. Again, you could probably figure out very reasonably what the sex of this penguin is based off its 4 features here and based off its known species. So I'll leave that, as the mathematics book always says, as an exercise to the reader. We leave it there. All right, let's do a little bit of visualization here just to explore it. Maybe we could do a pair plot. So we can say SNS pair plot of the data frame where hue is equal to species. And this would begin to explore the continuous feature columns. So what's actually happening here, I'm just comparing all the features to each other and then the features, the distribution amongst themselves. So what we can see here is for some features, they're very separated. Specifically, it looks like Coleman length, and this should probably be Coleman depth. So what does this actually tell us as machine learning practitioners? The beaks of the penguins are very different between the species. So there's a lot of information here. As far as flipper size, where are the flippers here? Flipper length. It looks like the Gen 2 penguins. Those are quite different based off their flippers, but these chinstrap and Adelie penguins, probably Adelie. These Adelie penguins and these chinstrap penguins, they're quite similar based off their flipper length. But luckily, their beaks are quite different. So this should be pretty good to separate on. Just even eyeballing this, we can kind of tell already we're going to have a pretty easy time, which means I would expect very few misclassifications. And look at this body mass difference here as well. You can see here that the 3 penguins weigh substantially different, which is kind of interesting on how different these body masses are versus like their flipper length here. Okay, so it means like there's these 2 penguins that kind of weigh the same but have like different flipper lengths. Okie dokes. So if you want, you could keep exploring this. Remember, we have the entire sex column as well. So you could begin to explore if maybe you were working with some penguin researcher on this and they said, oh, can you give me more information about the difference between not just the species, but male versus female in the species? You could begin to kind of get fancier here and do what's known as a cat plot. A cat plot, the way this works is you pass in your data frame, df, and then you decide that you want to build a grid. So you could say, okay, on my x, report back species, and on my y-axis, report back, let's say something like Coleman length. Maybe that's what you were interested. Or let's do body mass in grams. Say body mass in grams. And then you have to specify what kind of plot you want to do. So you could say kind is equal to box. So if I run this, this should give me a box plot. Okay, so I'm going to zoom one level out so we can see all this. So if I zoom one level out here, I can see that this is just the kind of hard-coded way of creating a box plot. I could also use seaborn box. But what's nice about using cat plot is I can begin to define columns. So I can do an extra separation. And you can check out the seaborn lectures that are already up for more information on this. But obviously I can see this particular penguin weighs a lot more than the Adelie and chinstrap species of penguins. So let's compare male versus female penguins. Is there a big weight difference there? So we can say, column is equal to the sex feature. And so what that does, it's going to automatically separate out two box plots for you into two columns, where the columns are defined as male versus female. And recall, we had that penguin that was a Gen 2 species where we didn't know its sex. So if I scroll back up here, remember I had this guy who, for whatever reason, I didn't record his sex or her sex, but I did know that their body mass index was 4,875. So I could come to this box plot and see, okay, if someone is 4,575, are they likely to be male or female? You can see that that's kind of at the lower end of the male and right in the middle of female. So even just based off the weight, I could have gone back and said, you know what, that penguin's very likely to be female. And then I could also look at the flippers, etc. But what you want to avoid doing, in my opinion, is build so many models on top of models, especially if you're just doing this for one penguin, right? It's probably easier just to drop that penguin. But that's to give you an idea of how you could make a reasonable assumption to kind of fill out that penguin's missing information. All right. So we're going to do a little bit of feature engineering here to deal with these issues of categorical columns, and then we'll continue off. All right, so what are we going to do here? I'm going to do the following. We're going to say, if we check out our current data frame, we have this island, and we also have this sex column. So let's just go ahead and do the following. Let's start separating it out into X's and Y's. Which feature is not helping much seeing data set originally according to you? I'm not sure I understand that question. All the features, we don't know which features are useful and which features are not yet. We can kind of see from the pair plot which features are very strong features. So if there's a lot of separation between these three color groupings, that's a good feature to look at. So clearly Coleman length is a strong feature, and so is Coleman depth. So as I mentioned before, their beaks are very different between the penguins. We don't know yet if the decision tree will think the same thing, but it's quite likely it's going to treat the beaks as a very important factor. So something we can look at is if we begin to plot this out, will it take a look at beaks first, or will it take a look at flippers first, etc. So what we're going to do here is we can begin to define some of these guys as, let's say, y is equal to df of species. So I have y now, and let's define x as df drop my species column along axis is equal to 1. So I have x here, and then what I'm going to do is I'm going to go ahead and get the dummy variables off of this. So I have these islands. What I'm going to do is just convert these into dummy variables by saying the following. I'm going to say pd.getDummies. of x. And if I just run this, notice what's going to happen. It's actually kind of super powerful. It keeps all the continuous features the same, but it creates some feature engineering for us, which is essentially just creating zeros and ones out of the categorical features. So 0 and 1 is this female, 0, 1 is this male. Now, if you've gone through some of the course already, you know about something called the dummy variable trap or multi-collinearity. All that is the fact that if I know in this particular data set that I have a 0 for female, then by default, that means male is 1. So you can Google search the dummy variable trap. So you can Google search dummy variable trap. I just put it in the chat here. But essentially all that's trying to say is you actually don't need both of these columns, right? One entirely encodes the information of both. So that's why if you look at PD get dummies, it has drop first as true as a parameter you can pass in. So if you run that, it will go ahead and just drop the first instance of this. So that way you only keep one of these features. So it's going to be sex male, and then only keep 2 of those islands. Because recall, this is actually encoding the same amount of information, because if it's not sex male, 0, then in theory, it's going to be female. So we don't actually need to pass in that information to our machine learning model. Okay, PD get dummies, that's ready to go. Let's define this as x. So I'm going to run that. So now I have my x features ready to go. Okay. Now, if you recall, if you were on last week's stream, recall that we had to scale the features, right? Last week we talked about support vector machines, where they're kind of using hyperplanes to separate out features, which means we probably had to scale them. But let's really think about what's happening at each node in the decision tree. Each node in the decision tree is just going to be looking at one feature, right? For example, one node is just looking at body mass index for the entire data set. Does that node care if that single feature is scaled to all the other features? Not really, right? It's just going to choose a number. So it's going to say, is body mass grams greater than or less to 2,000 or something like that. That node doesn't actually care if you were to scale them. Then it would just say, okay, is body mass index, or is body mass in grams less than or equal to 2 grams because you scaled it, or 2 units, etc. So we actually don't really care about scaling data with decision trees, which is kind of interesting, right? Because we're only considering one feature at a time in these nodes. So we don't actually need to scale everything. Unlike other machine learning algorithms that are highly geometry based. This is just kind of a brute force, look at these features, split them. Look at these features, impurity, split them, etc. So in that case, we're actually ready to go to separate this out into a training set and test set. So I'm going to do that. Let's say from sklearn.model selection, import train test split. This is going to split this up into a training set and test set so I can evaluate everything that's going on here. And so what we're going to do here is say train test split, shift tab, scroll down till we get to this guy. If you've been watching the machine learning lectures, you've seen me do this a million times already. I'm going to come back up here and paste it. This just is to make sure I get this tuple separation correct. So I do a train test split of x and y. My test size, I'm going to set my test size to, let's say, 30%. And my random state, let's set it to 101 just to be consistent with the lectures. There we go. So this will separate out my feature and my label into a training set, x train and y train, and a test set, x test and y test. Run that. You have to take it on a model by model basis. You can easily Google search which models need scaling. I'm trying to think if there's other ones. I mean, obviously any tree-based methods like random forest are also going to be immune to it because it's just other decision trees. But I kind of don't want to list off the top of my head which ones are immune to scaling because I'm probably going to miss one. So just take it on a, I would say if you're unsure, scale, because it doesn't make a difference to the decision tree whether you scale or not. Okay, So from sklearn.tree, import decision tree classifier. There's a question here. If I were to pass that information, I'm not sure what Kingbok is referring to. What information? Maybe you can answer that. Okay, so we say from sklearn.tree, import decision tree classifier. There's also a decision tree regressor, but I want to predict classes here, right? Which of the three species this penguin is. So that's a classification algorithm. So then we'll say model is equal to decision tree classifier. And as I always say, if this is the first time you're using a model, definitely explore the documentation for it. You can see right here that the criterion by default is the genie, impurity, and there's a ton of stuff that we can begin to play around with. You can also choose the maximum depth of the tree, the number of samples needed to actually split a leaf. So for example, in that spam or URL, at a certain point, you end up with like just 3 emails in a node. And so what you can decide is if there's a minimum number of samples you need in order to split again. So in this particular case, as we split the penguins on different features, if at a certain point we hit some sort of threshold of like, let's say there's only 5 penguins left, you could decide, okay, at a certain point, if there's only 5 penguins, set that to be a terminal node instead of splitting again on another feature. So in this particular case, the minimum samples needed to split are 2, which is kind of just saying, even if there's 2 penguins there, if you can figure out a way to split those again, go ahead and do it. Keep in mind, that could begin to lead to overfitting if you're splitting on like every single penguin. It's unlikely that the decision tree will try to do that. It really depends on your training data set. Other things to consider here are maximum number of features to consider. If you say none, I think it just considers all of them, etc. You could also try to get very fancy and think of the minimum impurity necessary to split. So thinking of not just the number of like penguins left, but also the genie impurity value. What's the minimum that you would want in order to continue splitting? Lots of stuff here. We're going to leave all of it at the default right now. That way we can see the results with the default and then begin to play with the results as we explore more of these. You can also see that entropy is another option. That is the information gain criteria. So entropy for information gain. Genie impurity is what people in the CART approach figured out, that those 2 professors from Berkeley and 2 professors from Stanford. Entropy for information gain is what John Ross Quinlan figured out with his ID3 C4.5 and C5.0. So you can always kind of play around with these, do cross-validation, figure out which is the best choice for criterion. Lots of different options you can begin to figure out here. Okay. So I just created my decision tree model. I'm just keeping the defaults for now. Let's go ahead and fit this to X-train and Y-train. And then I'm going to say base prediction is equal to, base underscore prediction. I'm calling it base prediction because this is like the base model. We'll say this is predict off X test features. And now I should see a bunch of predictions for this test set of all the species. How well do we perform? Well, I want to compare those base predictions to my known values, which is my y-test. So lots of different ways we can do this. We'll say from sklearn.metrics, import the confusion matrix. In fact, let's just import plot confusion matrix, actually. That's a little nicer. I'm going to say import plot confusion matrix, and let's also import the classification report. So I'm importing plot confusion matrix and classification report. You should be able to tab autocomplete these. And what I'm going to say is plot the confusion matrix. Quick note, for plot confusion matrix, it actually takes in your model. So instead of taking your base predictions, you pass in your model, your X test, and your Y test. And it will automatically pass in X test to your fitted model and compare the results to Y test, and then it plots them out. So this is our confusion matrix. How well are we doing here? We're doing pretty freaking awesome, right? We're only misclassifying in total 4 penguins. So 1 here, and then 2 here. But overall, we're doing pretty darn good. If we actually want to get metrics on this, we could say print classification report, y-test, and base predictions. And here we can see our classification report of precision and recall for each of these. We can also get our overall accuracy of 96%. So 96% of the time we're correct. And overall precision recall, it's pretty darn good. Luckily, this was a balanced data set where we had about as many penguins from each class as necessary. Or not as necessary, but you get the idea of what I'm trying to say. Okay, so what is one of the best things about decision trees? Well, let's start with one of the downsides of decision trees. One of the downsides of decision trees is you only get one tree, which means you only get one root node. So no matter what sort of analysis or feature engineering you do, when it comes to this decision tree, if you're only going to make one decision tree, you only get one root node, and it's like, you better hope that was a good root node because the Genie impurity mathematics is going to set automatically one of these as a root node no matter what you really do, right? So what do we actually do here in this case? Like why would we even use decision trees? If you have a lot of problems with that root node, what you could do is build out multiple decision trees and then swap out different root nodes and see how that affects your overall performance. That is for another day where we talk about random forest. But that's essentially the idea behind random forest is, oh, I'm going to start building out multiple decision trees and think about it that way. So clever ideas. However, let's toss all that aside because we're dealing with a single decision tree. So you might be wondering if there's really cool methods like gradient boosted trees or random forests. Why bother with this decision tree? So the main, the huge thing that the decision tree has going for it is it's super interpretable by a human. A human can look at a decision tree, and this is definitely not the case for almost any machine learning models beyond like linear regression, I think, is you can look at it and say, I know exactly what this machine learning algorithm is doing, and I can literally see it. There's a question on how do we know which feature is used for a root. I'll show you in just a second. We'll actually be able to display the decision tree. So more than almost any other machine learning algorithm, this one is super interpretable. This is basically what my little rant was about. So let's go into interpreting it. How do we actually take advantage of the fact that we're using the decision tree? It's usually not the strongest performing machine learning algorithm, but you trade that off for the interpretability of the algorithm. It's almost like a human did this for you, beyond the calculation of Genie impurity. But we saw that it wasn't actually that hard to do it ourselves manually. Okay, once you have a trained model, you can ask it, what are the feature importances? And it's essentially going to, based off those impurity values, tell you, I think these are the relative values of which features contain the most information. And what's easiest is if you just compare these values to each other. However, you notice there's actually no features here. It's just the values themselves. And I think there was a question by Kingbach saying, how would passing the information affect? You should be able to actually pass in the non-drop first version. And the way it would affect it is it would just give you slightly more information here on the feature importances. It would show male and female as a feature importance instead of just not being male. Whether or not that's useful to you, that kind of depends on what your situation is. In theory, it's the same information, just presented differently. It shouldn't drastically destroy your decision tree. So in theory, it should be fine to change that. Can you change the feature for the root? Not really, because it's calculated based off Genie impurity, right? Nor would you want to. You want the decision tree to mathematically figure out the best. Right. Anyways, I keep mentioning feature importances. These numbers are not useful themselves. What I really want is to compare them to my X columns, right? So these feature importances are linked up to these columns themselves. The easiest way to link these together is through a data frame. So what I like to do is I say PD data frame, and I pass in my index as x.columns, and then my data is equal to this model.featureImportances, and then I set columns equal to the string feature importance. And I'm going to zoom out because it's kind of a long line of code. So what am I doing here? I'm basically just saying I'll use this values as my data, this list of values, and these columns are going to be my index. And then this column is actually just the name that I'm giving this data frame. So you run this. If your results are slightly different, it's very possible you didn't use the same random split I did. Maybe you use 0.33 and random state of 42 instead of 0.3 and 101. Another question here, we have entropy or genie in terms of making a good decision tree. Here's a crazy idea. Try both and see which one performs better. There's no way I'd be able to know that without knowing your data. And we'll get into showing and visualizing a tree in just a second. But this is super important here. This is, again, very nice to see how interpretable this is. Remember I mentioned, hey, these beaks are actually very differentiated between the penguins, right? I already knew, scrolling up here, that the culmen length and culmen depth for certain penguins was very different. And luckily, it looks like my model thought the same thing. It said, hey, culmen depth is pretty important. But it also said, hey, flipper length is pretty important, which if we scroll back up here, we could check that out as well. So where's flipper length? Flipper length right here. So we can see flipper length versus culmen length. That essentially is where we get the most separation between these classes. So my machine learning model, the decision tree, thought those were actually quite important. What's kind of interesting here is it didn't give much importance to body mass in the grams. And that is also kind of dependent on how it's ordering the splits, whether or not it's gaining more information there. And that's probably due to the fact that two of the species had very similar weights. If we scroll back up here to our box plot, sorry, I'm keep scrolling back up and down. Recall that according to the body mass index, if let's remove this column sex, so we're only considering the species themselves. It's really only for this particular species of Gen2 or Gen2 where the body mass made a difference. The body mass, I keep saying body mass index, the body mass in grams of the Adelai and chinstrap species were actually almost the same, right? So you're not really gaining that much information. And it's very likely that you could just use beak difference and flipper difference to separate out this class, which is probably what the decision tree figured out itself. And it said, oh, you know what? I'm not even going to, at the end of the day, I'm doing so well in classifying without body mass, I'm not even going to give it that much of a thought. Okay, so we keep saying, like, this is highly interpretable. I should be able to see the tree. If you want, you can actually plot this. You should be able to make a bar plot here by saying dot plot. Let's see, dot plot, I think kind is equal to bar. There, so you can actually begin to see this feature importance here visually. This is just the same numbers visually interpreted. Okay, let's actually show you how to visualize a tree. Luckily, with the latest version of scikit-learn, this is super easy. We simply say from sklearn.tree, import plot tree, and we say plot tree, and you just pass in your model. Because really, when you think about what is the model itself, the model is just a series of rules of features. The model is just sitting there with a bunch of rules. Let me plot this out, and it's this right here, right? Now you might be thinking, how the heck am I supposed to read this tiny decision tree? Well, luckily, what we can do is we can expand the figure size. So first off, you get a crap ton of text. Put a semicolon here. That gets rid of the text. And what we're going to do here is if you imported matplotlib.pyplot, say import matplotlib.pyplot as plt, in case you haven't done that at the top already. Once you've done that, we'll say plt figure, and you can set fig size equal to something much larger. I think I set 12 by 8, and we can also set a higher DPI. That's dots per inch. So run that, and now you should see a really nice tree. So for me, I'm always super impressed by this. This is freaking awesome, if you ask me. Because it shows you all that information that we just discussed theoretically in the slides, right? And it shows you a ton of information. It's showing you the feature. It's showing you the genie impurity, the number of samples at that particular node, and then what the values are here. Those are the instances per class. And you might be thinking, is there any way that I can begin to make this even more informative? One way is in plot tree, you can say filled is equal to true. And what it's going to do is it's actually going to fill these out based off the features. And what you can also do is decide on the feature names. So instead of x2, I could say my feature names are equal to x.columns. And for whatever reason, I think this should be the default, but whatever. In my opinion, like this should be the default output of plot tree instead of that crazy amount of text and then those black and white things that are hard to interpret. But what's nice about setting up like this with a larger figure size, filled is true, feature names is equal to X columns, this is like the most human interpretable thing of all time, right? I can see exactly what it's doing. So interestingly enough, based off genie impurity here, it's deciding that there's a lot of information to be gained here based off splitting the flipper length on 206 millimeters, splits that again, and you can see then it's looking at Coleman length over here, and it looks at it again at this orange, and then it also says like what island did you find these guys on, etc. And what's really interesting is that actually you'll see that none of these features actually consider the grams of the penguins. So what you could do is begin to play around with things like information gain, genie impurity, etc. to try to see if it'll then begin to consider stuff. So one of the things we can do is I'm going to copy and paste most of this code into what I call a report model function. So this is what I'm going to do here. I'm going to say the following. I'm going to say df report model takes in a model, and then it does the following. It's going to say model predictions is equal to that model that's passed in and predict off of X test. This is just a nice function to work with. And then I'm going to say plot the confusion matrix. So plot confusion matrix, what was I going to say? Plot confusion matrix off the model. Actually, let's just print the classification report. We'll say print the classification report, y test, model preds. And then I'll print a new line. And then we'll also say PLT figure plot tree. So why am I doing this? This is just for, it will print out the classification report and plot the tree for any model that I pass in. Why would I want to do this? Just to explore and understand the different hyperparameters. So recall that our model used the base hyperparameters. So what I'm going to do is let's create a new model that sets a max depth. Let's go ahead and report this model real quick just to test our function. I'm going to say report model, the model we currently have. So this reports out the confusion matrix and then also plots out the tree. Quite nice, right? Let's create a new model that maybe is a pruned tree. So what do I mean by pruned tree? Recall that if I wanted to, I could cut off these splits and have this be a leaf node. So I could say pruned tree is equal to a decision tree classifier where I say my max depth that I allow is only 2. And then I'm going to fit this pruned tree to my training data, xtrain and ytrain. Okay, so once I have that going for me, let's go ahead and report this pruned tree model and see what this looks like. So it performs a little worse on some of these, and if we take a look at why, it's because at most we're pruning the tree, right? We're not letting it actually maybe possibly overfit. So pruning is important if you think your model is overfitting, and you can check if your model is overfitting by comparing your performance on training data versus test data. And you could also then begin to play around with the max depth here. Hopefully your mind is now thinking of a cross-validation, a grid search, that sort of thing. You could easily perform a grid search to figure out what's the best max depth or something like that. So if I say max depth is equal to 1, like the shortest tree possible, I actually get huge errors here because it's not able to even find chin strap. But this is a depth of 1, right? Basically only allow for 1 split or 1 level down the tree. In general, you probably would not do this. This is like the URL example that we showed in the slides. So we probably want it to go a little higher, or maybe you just want to like let it explore really deep trees, etc. If it can't gain any more information by going deeper, the max depth is not a guarantee of depth. So if I said max depth is 200, that doesn't mean it's going to go 200. It's just you're basically setting a limit of how deep it can go. There's also max leaf nodes. so I'm going to edit that. Max leaf nodes essentially says I'm only going to allow this many leaves over the entire tree. So to make that really obvious is we can say max leaf nodes is equal to 3. So how many penguins do I have? How many penguin types? I have 3 penguin types, right? So if I only allow 3 leaf nodes, that means I'm going to try my best to separate these out as quickly as possible. So this is technically not really a pruned tree because I'm kind of defining it based off the leaf nodes. But just to show you visually, if I say max leaf nodes is equal to 3, that means I only get 3 leaf nodes. I get this guy here, and this guy here. So those are my 3 leaf nodes. I can also begin to play around with criterion. Maybe we want to make an information or entropy based tree. So I can come back up here. Let's just call this entropy tree now. Or let's call it IG tree for information gain tree. So we're going to say IG tree is where my criterion is equal to entropy. Remember, that's what Quinlan was working on with his ID3, C4.5 trees. Maybe that performs a little better. We don't know yet. And let's run this, fit it, and plot its results. So we run this. This is now based off entropy or information gain. You'd be able to compare the raw results here, and you'd be able to compare the tree. Notice now information gain is actually starting to pick up some different features. It looks like it is considering whether the person is male or female, which is kind of interesting, or the penguin is male or female, in order to do this hopefully a little better. If we compare the results here, I think it performs roughly the same as this one. Let's see, 96% accuracy, 95% accuracy. Yeah, they're kind of just trading off between the classes themselves. And you could plot a confusion matrix to get an idea of that. But what's really nice is we have this report model functionality, which really allows you to play with this. And that's kind of it for today's lecture. So what I would encourage you to do is get this report model, get the scikit-learn documentation on decision trees, and just start playing around with it. See how it actually affects the visualization of the model. This is a simple enough data set where you can really understand those things. Play around with the feature engineering and just see how it affects the model. But that's pretty much what I wanted to stream today. Any last minute questions? Let's see here. Thanks everyone for watching this. Paul's question, it's possible that I'd have to see your code to really understand what's going on, Paul. That's surprises to me that it would do a different tree. Especially, maybe put everything in the same cell, Paul, run it twice and see if that's still the effect. What value of genie is good? That question doesn't really make sense, right? There's no good or bad value of genie impurity. It's just a measure of how much information is contained within a particular feature. And you, as the user of scikit-learn, you don't really care about the actual value of genie impurity. You just care about if you're using genie impurity versus using information gain. In case of continuous features, how does it come up with a number at which the node splits? So that's a good question. I'm actually going to record a separate lecture on that because it is slightly different. I'll record a lecture and that'll be part of the course when we start uploading decision trees. It's kind of like a next set of slides. It does use genie impurity. It just basically does, it compares if I split at this value versus splitting at like this value, how much information do I gain? So it kind of just tests a bunch of different values to split on for the continuous feature. So if your range was like from 1 to 10, it'd be like, oh, should I split at 1, 2, 3, 4, 5, 6, 7, etc. Until it finds like the optimal thing. It's based off that error criterion we actually saw at the very beginning, which was y predicted versus the true y squared. So it uses an error metric to figure out which is the one that's going to minimize that error. I see someone saying higher the genie, the better. I think you're thinking about it. Well, it depends on what you're actually what question you're trying to answer. I think just the question itself of what is a good genie impurity is not one that's like super useful in practice. You shouldn't be like trying to go for a particular value of genie. You should let the algorithm figure out the best ordering. It's just a measure of information. No, you cannot take more than 2 features at a node. Each node is essentially a feature. Any other questions here? Above 96%, could it be less accurate or more accurate on test data in order to tell it overfitting or not? As far as overfitting is concerned, you should be getting roughly the same performance as a training set on your test set. That is how you figure out if something is overfitting. And you can check out, we have lectures on overfitting and understanding it in the course. Yeah, cool. I think that's it. We're kind of done here. I'm going to bring over this so I can see. Okay, so I'm going to start typing out. Thank you, everyone, for watching. Keep an eye out this week for uploads of tree-based method lecture videos, including decision trees, random forests, and boosted trees. All right. I think that's it. All right. Cheers. Thanks, everybody. Looks like the delay wasn't too bad from what I'm seeing. Okay. All right. I'm going to end the stream now, but thank you, everyone, for coming and watching.